Hello CCP2 students, this is a video now on experiment number 6. This is the one we actually did the data, and like I said before in the end of the last video, you were supposed to go and copy your data from your OneNote in the handouts folder where it says labs and copy page 9 to page 9 so we have it in front of us. So let's do it. So I'm going to use Anna's as an example, and I'm going to see if I can put it on mine or whatever like that. So let's go to it. So handouts. Okay, so this is Anna's page 9. So now what we're going to do, let's go to the data here on the next page. Okay, so let me tell you a couple things. So number one, let me write down the reaction again. Let's see here. Write it down in more precise terms for you guys so you can see it. So what we had for the reaction, so we had ethanoic acid, also known as acetic acid, COOH, plus basically propanol. Oops, CH2, CH2OH. And our products are going to be actually CH3, COO, CH2, CH3, and H2O. All right. So what we want to get a handle on is how much do we have of this reactant at the beginning and how much do we have at the end, because it'll help us do an ice table to figure out what our equilibrium concentration is when this reaction helped get to equilibrium. So what did we do? What we did was we started the reaction. We basically mixed acetic acid with isopropanol, and then we measured how much of the acetic acid was there by doing a titration. So we're trying to figure out how much reactant do we have at the beginning. So here we titrated the acetic acid versus NaOH, okay? And so from the number of moles of NaOH we added, we can figure out how many moles were present in our reaction flask of acetic acid. So again, what we're trying to do is figure out how much we have of this by titrating it. So in your book, it shows that earlier in this lab thing, we had NaOH, and we get water, and we get CH3, COO minus Na plus. So anyway, we get the conjugate base and stuff like that. So what we want to do then is figure out how many moles of NaOH was consumed. So the big thing I have to tell you is this. Your NaOH concentration was 0.5 molar. So what we're going to do then, how do we get to moles of NaOH consumed? We take the 0.5 molar times the amount of liters that happened in the titration. So we did 2 trials, as Anna shows up here. First trial we saw we did 7.6. We call it trial 2, but we'll call it trial 1 for the next one, and 7.0. So over here, we'll take 0.5 times 0.0076, and then 0.5 times 0.007. Okay, so let's put that in there. And whatever number of moles we get is also the number of moles of acid we had. So for every mole of base we add into this, we have exactly 1 mole of this. Okay, so let's do this calculation real quick. If I can find the calculator. Okay, 0.5 times 0.0076 equals 0.0038. So I'll put 0.0038 moles. That means we had 0.0038 moles in our titration. Okay, then let's do the 0.5 times 0.007. 0.5 times 0.007. 0.5 times 0.007 equals 0.0035 moles. Now, by the way, that's 0.0035 up here too. Now, guess what? Here's the thing. Here's the thing that's kind of confusing. When you did this, which was a long time ago, what you did was you only took 1 milliliters. You only took 1 milliliter of your reaction vessel out. So in reality, excuse me, the number of moles you had, excuse me again, you're going to have to, as it says, your sample size was 0.001 liters. So this was titrated against the sample size of 1 mil. What was our total sample size that we did? And it turns out we have 33 mils. Let me show you where we got that. So we only titrated 1 mil of our thing. So over here, our reaction was 14 mils of this plus 19 mils of that. So we had 33 mils. So this is how many mils, this is how many. So in essence, we have to multiply this by 33, this number of moles, because this is moles per, actually, let's do this. Let's put a point per 0.001. Okay, so let's put 0.0038 divided by 0.001. And if we do that, we're going to come up with, I believe, 3.8 molar and 3.5 molar. Okay, why did I do that again? Because I only put in 1 milliliter of this. So in 1 milliliter, I had this. So in a liter, I would have 1,000 times that. So let me say that again. When we did the titration, we only took out 1 milliliter of our reaction. So we have 0.0038 moles of acetic acid in basically 1 milliliter. So if we want to put it in molar, which is per liter, we have to divide our moles by our volume we have, which is 0.001. So this is our actual molarity. So our average molarity is 3.65 molar. Cool. Now, let's go to equilibrium now. Same sodium hydroxide solution, by the way. But this time, we're only adding a couple mils. So we got 2.9 and 2.8. So we'll put in, okay, so we put 0.0029 or 0.0028 liters. So it's 2.9 milliliters or 2.9 times 0.5. And then we have to divide that by 1 milliliter again. So let me do that. I know these calculations are really hard sometimes to figure out why we're doing it the way we're doing it. Times 0.5 equals, divide that by 0.001 because we only did 1 milliliter. Now we're down to 1.45 molar. And for this one, let's see. Sorry, go back to my calculator. Let's do 0.0028 times 0.5 equals, divided by 0.001. That can be much different, 1.4 molar. So our equilibrium concentration of acetic acid is 1.425. Okay, now we can do our ice table. Because we're going to use this for our initial and this for our ending. So the key thing in this equilibrium table is if we put in let me enlarge this a little bit. We put in 3.65 here, our average, and we put in 1.425 here. I'm sorry, we got 1.425 at equilibrium. We can figure out our x, and x is going to be really important actually. So our x is, what is 3.65 minus 1.425? 3.65 minus 1.425 equals 2.225. 2.225. And by the way, our initial concentration of this should also be the same, 3.65, 2.225, We're going to assume it's the same because they're put in the same ratio, by the way. So now we put over here x, our change in x, everything's 1, by the way. We're going to put our change in x as plus 2.225 plus 2.225. Then we get 2.225 and 2.225. So now equilibrium concentrations, what do we have? We're going to put products over reactants. We're going to put 2.225. That's our concentration of product 1. 2.225 for our water. And we're going to put that over 1.425 times 1.425. Okay, so what do we get? Let's do our equilibrium constant now, which is what we're looking for in this experiment. Say 2.225 Okay, so that's what that is. I'll divide it by 1.425 equals, and divide that answer by 1.425. So we get our equilibrium constant is 2.44. So our KEQ came out to be 2.44. Okay, let's now discuss what that means. Okay, so I don't know. You can show some of your calculations, but now you know what you're doing with that one. Assume that the reaction for the survey was exothermic. How would lowering the temperature affect the equilibrium concentration of the acid? Well, very good. We're doing some Le Chatelier's principle here. So, let's see here. If it's exothermic and we have heat on this side, so we have our acetic acid plus our isopropanol. Then we make our product plus heat. If we lower the temperature, it would actually push it this way, wouldn't it? So if you take away heat by lowering the temperature, the reaction would go further right. So put further right to replace lost heat. Okay, use your results for KC to find the reverse reaction. Well, what was our number again? 2.44. So our KEQ was 2.44. You take the reciprocal, 1 over 2.44. So what is that? 1 over 2.44. 0.4, let's call it 0.41. Okay. And since we're not intimately familiar with what we did since it's been so long, let's skip that one. And that will be it for lab number 5. So again, I think we still learned something, even though we haven't seen it before for a while. We still had to review our equilibrium stuff and everything else. But I forgot to do one thing. Let's go back to the pre-lab, which we may or may not have done. So remember when you write equilibrium expressions, you put the products to the power of their coefficient over the reactants to the power of their coefficient. If and only if they're gaseous or aqueous. Do not include solids. Do not include solids. So now we're on page number 5. Let's go to page number 5 in your experiment. So this one would be concentration of N2O4. By the way, you can do concentration or pressure for gases. This would be over NO2 squared because of that 2. Now let's be careful this one. Do not include the water, because water is a liquid, doesn't change concentration. So we have H3O, concentration, to the 1 power. This one, it's an organic compound to the 1 power. It's actually acetic acid, I believe. And we put it over this is actually the conjugate base, I'm sorry, over the this acid. HC2H3O2. There we go. These are all gases, so this one would be NH3 to the 2nd power, because there's a 2 there, over H2 to the 3rd power, times N2 to the 1st power. And then it says, let's do number 1B. Let's calculate it In other words, take your equilibrium expression. You guys can do this. Plug all that crap in and see what the number is. Then this last question is interesting. In the reaction you're about to do, let me show you what that reaction is again. Sorry, you're going to be mad at me here for a minute. The reaction you're about to do makes water. Normally you don't put water in the equilibrium constant because water is water. There's no concentration to it. But here we're going to put in the concentration of water. Now, believe it or not, when you add stuff to the water concentration does go down, but only very, 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 very slightly, because it's always in so much excess. But since you're making water, and it's important to reaction, we include it. So how about if we just say, since we're making water, here's a lot more. Concentration of water changes more, and so we include it. That's all. Okay, now we're done with lab experiment 6. So hopefully that helped a little bit. It's a lot of stoic to finally get to the point where you can plug in molarities into your ice table. It's another excuse to do an ice table, but getting to actually plug in values was pretty contorted this time, but that's the way it is in real life. So that is it for today. Thank you.